In set theory, a branch of mathematics, determinacy is the study of under what circumstances one or the other player of a game must have a winning strategy, and the consequences of the existence of such strategies. Basic notions. Games. The first sort of game we shall consider is the two-player game, of perfect information of length omega, in which the players play natural numbers. In this sort of game we consider two players, often named I and II, who take turns playing natural numbers, with I going first. They play forever, that is, their plays are indexed by the natural numbers. When they're finished, a predetermined condition decides which player won. This condition need not be specified by any definable rule, it may simply be an arbitrary lookup table saying who has won given a particular sequence of plays. More formally, consider a subset A of Bayer space. Recall that the latter consists of all omega sequences of natural numbers. Then in the game GAR, I plays a natural number A0, then II plays A1, then I plays A2, and so on. Then I wins the game if and only if and otherwise II wins. A is then called the payoff set of GAR. It is assumed that each player can see all moves preceding each of his moves, and also knows the winning condition. Strategies. Informally, a strategy for a player is a way of playing in which his plays are entirely determined by the foregoing plays. Again, such a way does not have to be capable of being captured by any explicable rule, but may simply be a lookup table. More formally, a strategy for player I is a function that accepts as an argument any finite sequence of natural numbers, of even length, and returns a natural number. If sigma is such a strategy and less than A0, A2, N1 greater than is a sequence of plays, then sigma is the next play I will make, if he is following the strategy sigma. Strategies for two are just the same, substituting odd for even. Note that we have said nothing, as yet, about whether a strategy is in any way good. A strategy might direct a player to make aggressively bad moves, and it would still be a strategy. In fact, it is not necessary even to know the winning condition for a game, to know what strategies exist for the game. Winning strategies. A strategy is winning if the player following it must necessarily win, no matter what his opponent plays. For example, if sigma is a strategy for I, then sigma is a winning strategy for I in the game GAR if, for any sequence of natural numbers to be played by II, say less than A1, A3, A5, greater than, the sequence of plays produced by sigma when II plays thus, namely as an element of A. Determined games. A game is determined if for all instances of the game there is a winning strategy for one of the players. Note that there cannot be a winning strategy for both players for the same game, for if there were, the two strategies could be played against each other. The resulting outcome would then, by hypothesis, be a win for both players, which is impossible. Determinacy. From elementary considerations, all finite games of perfect information in which draws do not occur are determined. Familiar real-world games of perfect information, such as chess or tic-tac-toe, are always finished in a finite number of moves. If such a game is modified so that a particular player wins under any condition where the game would have been called a draw, then it is always determined. The condition that the game is always over in a finite number of moves corresponds to the topological condition that the set A giving the winning condition for GAR is clopine in the topology of Bayer space. For example, modifying the rules of chess to make drawn games a win for black makes chess a determined game. As it happens, chess has a finite number of positions and a draw by repetition rules, so with these modified rules, if play continues long enough without white having won, then black can eventually force a win. It is an instructive exercise to figure out how to represent such games as games in the context of this article. The proof that such games are determined is rather simple. Player I simply plays not to lose, that is, he plays to make sure that player 2 does not have a winning strategy after I's move. If player I cannot do this, then it means player 2 had a winning strategy from the beginning. On the other hand, if player I can play in this way, then he must win, because the game will be over after some finite number of moves, and he can't have lost at that point. This proof does not actually require that the game always be over in a finite number of moves, only that it be over in a finite number of moves whenever 2 wins. That condition, topologically, is that the set A is closed. This fact, that all closed games are determined, is called the Gale-Stewart theorem. Note that by symmetry, all open games are determined as well. Determinacy from ZFC. Gale and Stewart proved the open and closed games are determined. Determinacy for second level of the Borel hierarchy games was shown by Wolff in 1955. Over the following 20 years, additional research using ever more complicated arguments established that third and fourth levels of the Borel hierarchy are determined. In 1975, Donald A. Martin proved that all Borel games are determined, that is, if A is a Borel subset of Bayer space, then G is determined. This result, known as Borel determinacy, is the best possible determinacy result provable in ZFC, in the sense that the determinacy of the next higher Wedge class is not provable in ZFC. In 1971, before Martin obtained his proof, Harvey Friedman showed that any proof of Borel determinacy must use the axiom of replacement in an essential way, in order to iterate the power set axiom transfinitely often. Friedman's work gives a level-by-level result detailing how many iterations of the power set axiom are necessary to guarantee determinacy at each level of the Borel hierarchy. For every integer n, ZFC, P proves determinacy in the nth level of the difference hierarchy of sets. But ZFC, P does not prove that for every integer n nth level of the difference hierarchy of sets is determined. See reverse mathematics for other relations between determinacy and subsystems of second-order arithmetic. Determinacy and large cardinals. There is an intimate relationship between determinacy and large cardinals. In general, stronger large cardinal axioms prove the determinacy of larger point classes, higher in the Wedge hierarchy, and the determinacy of such point classes, in turn, proves the existence of inner models of slightly weaker large cardinal axioms than those used to prove the determinacy of the point class in the first place. Measurable cardinals. It follows from the existence of a measurable cardinal that every analytic game is determined, or equivalently that every co-analytic game is determined. Actually, a measurable cardinal is more than enough. A weaker principle, the existence of zero hash, is sufficient to prove co-analytic determinacy, and a little bit more. The precise result is that the existence of zero hash is equivalent to the determinacy of all levels of the difference hierarchy below the omega-2 level, i.e., omega n pi 11 determinacy for every. From a measurable cardinal we can improve this very slightly to omega-2 pi 11 determinacy. From the existence of more measurable cardinals, one can prove the determinacy of more levels of the difference hierarchy over pi 11. Proof of determinacy from Sharp's Fourier. Every real number R determinacy is equivalent to existence of R hash. To illustrate how large cardinals lead to determinacy, here is a proof of determinacy given existence of R hash. Let A be a subset of the Bayer space. R equals P T for some tree T on. Given a partial play S, let B the subtree of T consistent with S subject to max 1 less than len. The additional condition ensures that is finite. To prove that A is determined, define auxiliary game as follows. In addition to ordinary moves, player 2 must play a mapping of into ordinals such that each new move extends the previous mapping. Then, the ordering of the ordinals agrees with the Klein-Brouwer order on. Recall that Klein-Brouwer order is like lexicographical order except that if S properly extends T then S less than T. It is a well-ordering IFF. The tree is well-founded. The auxiliary game is open. Proof. If player 2 does not lose at a finite stage, then the union of all is well-founded, and so the result of the non-auxiliary play is not in A. Thus, the auxiliary game is determined. Proof. By transfinite induction, for each ordinal alpha compute the set of positions where player 1 can force a win in alpha steps. Where a position with player 2 to move is losing in alpha steps IFF, for every move the resulting position is losing in less than alpha steps. One strategy for player 1 is to reduce alpha with each position, and one strategy for player 2 is to pick the least move that does not lead to a position with an alpha assigned. Note that L contains the set of winning positions as well as the winning strategies given above. A winning strategy for player 2 in the original game leads to winning strategy in the auxiliary game. The subtree of T corresponding to the winning strategy is well-founded, so player 2 can pick ordinals based on the Klein-Brouwer order of the tree. Also, trivially, a winning strategy for player 2 in the auxiliary game gives a winning strategy for player 2 in original game. It remains to show that using R#, the above-mentioned winning strategy for player 1 in the auxiliary game can be converted into a winning strategy in the original game. If the auxiliary response uses only ordinals with indiscernibles, then the moves by player 1 do not depend on the auxiliary moves, and so the strategy can be converted into a strategy for the original game. Suppose that player 1 loses in the original game. Then, the tree corresponding to a play is well-founded. Therefore, player 2 can win the auxiliary game by using auxiliary moves based on the indiscernibles, which contradicts player 1 winning the auxiliary game. Wooden cardinals. If there is a wooden cardinal with a measurable cardinal above it, then pi12 determinacy holds. More generally, if there are n wooden cardinals with a measurable cardinal above them all, then pi1n plus 1 determinacy holds. From pi1n plus 1 determinacy, it follows that there is a transitive inner model containing n wooden cardinals. Determinacy is equiconsistent with a wooden cardinal. If determinacy holds, then for a Turing cone of X, L, X satisfies OD determinacy, and in HODL, X is a wooden cardinal. Projective determinacy. If there are infinitely many wooden cardinals, then projective determinacy holds, that is, every game whose winning condition is a projective set is determined. From projective determinacy it follows that, for every natural number n, there is a transitive inner model which satisfies that there are n wooden cardinals. Axiom of determinacy. The axiom of determinacy, or AD, asserts that every two-player game, of perfect information of length omega, in which the players play naturals, is determined. AD is provably false from ZFC. Using the axiom of choice one may prove the existence of a non-determined game. However, if there are infinitely many wooden cardinals with a measurable above them all, then L is a model of ZF that satisfies AD. Consequences of determinacy. Regularity properties for sets of rails. If A is a subset of bare space such that the Banach-Mazur game for A is determined, then either 2 has a winning strategy, in which case A is meager, or I has a winning strategy, in which case A is comeager on some open neighborhood. This does not quite imply that A has the property of bare, but it comes close. A simple modification of the argument shows that if gamma is an adequate point class such that every game in gamma is determined, then every set of rails in gamma has the property of bare. In fact, this result is not optimal. By considering the unfolded Banach-Mazur game, we can show that determinacy of gamma implies that every set of rails, that is, the projection of a set in gamma, has the property of bare. So, for example, the existence of a measurable cardinal implies pi11 determinacy, which in turn implies that every sigma 12 set of rails has the property of bare. By considering other games, we can show that pi1n determinacy implies that every sigma 1n plus 1 set of rails has the property of bare. Is Lebesgue game measurable and has the perfect set property? Periodicity theorems. The first periodicity theorem implies that, for every natural number n, if delta 12n plus 1 determinacy holds, then pi 12n plus 1 and sigma 12n plus 2 have the Prull ordering property. The second periodicity theorem implies that, for every natural number n, if delta 12n plus 1 determinacy holds, then pi 12n plus 1 and sigma 12n have the scale property. In particular, if projective determinacy holds, then every projective relation has a projective uniformization. The third periodicity theorem gives a sufficient condition for a game to have a definable winning strategy. Applications to decidability of certain second-order theories. In 1969, Michael O. Rabin proved that the second-order theory of n successes is decidable. A key component of the proof requires showing determinacy of parity games, which lie in the third level of the Borel hierarchy. Wedge determinacy. Wedge determinacy is the statement that for all pairs A, B of subsets of Bayer space, the wedge game G is determined. Similarly, for a point class gamma, gamma wedge determinacy is the statement that for all sets A, B and gamma, the wedge game G is determined. Wedge determinacy implies the semi-linear ordering principle for the wedge order. Another consequence of wedge determinacy is the perfect set property. In general, gamma wedge determinacy is a consequence of the determinacy of Boolean combinations of sets in gamma. In the projective hierarchy, pi11 wedge determinacy is equivalent to pi11 determinacy, as proved by Harrington. This result was extended by Hjorth to prove that pi12 wedge determinacy already implies pi12 determinacy. This subsection is still incomplete. More general games. This section is still to be written. Games in which the objects played are not natural numbers. This subsection is incomplete. Determinacy of games on ordinals with ordinal definable payoff and length omega implies that for every regular cardinal kappa greater than omega there are no ordinal, definable disjoint stationary subsets of kappa made of ordinals of cofinality omega. The consistency strength of the determinacy hypothesis is unknown but is expected to be very high. Games played on trees. This subsection is still to be written. Long games. Existence of omega-1 wooden cardinals implies that for every countable ordinal alpha, all games on integers of length alpha and projective payoff are determined. Roughly speaking, alpha wooden cardinals corresponds to determinacy of games on rails of length alpha, assuming a limit of wooden cardinals kappa with O equals kappa plus and omega wooden cardinals above kappa. Games of variable countable length where the game ends as soon as its length is admissible relative to the line of play and with projective payoff, are determined, assuming that a certain iterability conjecture is provable. Existence of a measurable wooden cardinal implies determinacy of open games of length omega-1 and projective payoff, relative to a wooden limit of wooden cardinals and a measurable above them. It is consistent that every game on integers of length omega-1 and ordinal definable payoff is determined. It is conjectured that the determinacy hypothesis is equiconsistent with a wooden limit of wooden cardinals. Omega-1 is maximal in that there are undetermined games on integers of length omega-1 plus omega and ordinal definable payoff. Games of imperfect information. In any interesting game with imperfect information, a winning strategy will be a mixed strategy. That is, it will give some probability of differing responses to the same situation. If both players' optimal strategies are mixed strategies, then the outcome of the game cannot be certainly determinant. But the probability distribution of outcomes to opposing mixed strategies can be calculated. Against this definition, all finite two-player zero-sum games are clearly determined. However, the determinacy of infinite games of imperfect information is less clear. In 1969, David Blackwell proved that some infinite games with imperfect information are determined, and in 1998, Donald A. Martin proved that ordinary determinacy for a boldface point class implies Blackwell determinacy for the point class. This, combined with the Borel determinacy theorem of Martin, implies that all Blackwell games with Borel payoff functions are determined. Martin conjectured that ordinary determinacy and Blackwell determinacy for infinite games are equivalent in a strong sense, but as of 2010, it has not been proven that Blackwell determinacy implies perfect information game determinacy, quasi-strategies and quasi-determinacy.